error analysis. See, error analysis starts with the concept of accuracy and precision. And before accuracy and precision, just have introduction of this chapter. See, in every experiment, you will encounter some sources of error. Out of those sources, there are few sources that you can remove. Like these are the sources of error that you can control. Maybe your instrument is faulty, so you can take a better instrument. But there are sources of errors which you cannot control, like temperature. There are certain measurements which varies with temperature. Pressure, there are certain measurements which varies with pressure. So there are plenty of examples where you can not exactly control the error of experiment. So the best thing is to calculate that error. Like if you can report in an experiment that, okay, I did let's take a very basic experiment of measuring the length of a scale or length of a wire. If you can report that you measure the length of the wire to be 2 centimeter and there could be 5% of error. If you can report this error, then your reading is very accurate. Like you are exactly telling that this is the exact value. This is what you have measured. And the error bars are plus minus 5%. So whenever you do experiment, I'm not sure whether you have done experiments in this session or not. Whenever you do experiments, along with the measured value, you're supposed to report the error in your measurement. So in this chapter, whatever we'll study how to calculate error. Once you have calculated error, then you will learn how to combine it. Like you calculated that in quantity A, error is 2%. In quantity B, error is 3%. Then you will learn how to calculate error in A into B. So the error starts with the concept of, before starting error, let's discuss one more thing that's known as least count. Do you know what is least count?
0.01 centimeter.
That is for a particular instrument. What is exactly least count? Least count is the minimum measurement of an instrument. If I take an instrument, then the minimum measurement that can be taken from that instrument is known as least count. For example, if you have a scale, meter scale that you use to measure the length of the line over your copy. For meter scale, the least count is, what's the minimum value that you can measure through a meter scale?
1 centimeter.
Nah, not 1 centimeter. Say a meter scale have this 0, 1 centimeter, and then you have 10 divisions, right?
Yes.
Each division can measure 0.1 centimeter.
0.
That's one. So the least count of a meter scale is 1 mm. After meter scale, if I take another instrument, least count of Vernier Caliper. Have you used Vernier Caliper? No.
Yes, sir.
Yes, sir.
Where? Are labs
In
open?
practical.
You're doing practical?
No,
I mean,
teacher
online.
showed.
Okay. Virtual labs. Huh? So for Vernier Caliper, the least count is 0.01 centimeter. So it's basically 0.1 mm. So it can measure even smaller than meter scale. If you need even smaller measurement, we use a device which is known as screw gauge. It can measure even less, 0.001 centimeter. It's 0.01 mm. So these are the least count of few important devices. After least count, the next thing is accuracy and precision. So these are two definitions. One is accuracy and other is precision. See, it measure the closeness of your measured value with the true value. Closeness of measured value and true value. That's known as accuracy. Let's say I take a rod, for example. I take a rod and I tell you the true value, the true length of the rod is 10.2 centimeter. Then you have three observers. Each one of them measure this rod. A measure it to be 10.1 centimeter. B measure it to be 10.0 centimeter. C measure it to be 9.9 centimeter. So can you tell me which one is most accurate?
A.
A, because this measured value of A is very close to the true value. So that's accuracy basically. It measure the closeness between the measured value and true value. Precision is totally different than accuracy. It's basically measure how close the measured values are to each other. Measure closeness of measured values with each other. It's independent of accuracy. There's no relation between precision and accuracy. It is independent of accuracy. These have absolutely no relation with accuracy. For example, you have three observers, an observer A, an observer B, and observer C. Each one is taking some three sets of readings. So observer A takes three readings. It comes out to be 10.1, 10.2, and 10.3. Observer B also takes three readings. It comes out to be 10.01 centimeter, centimeter, centimeter. It's 10.01 centimeter, 10.02 centimeter, 10.03 centimeter. The third one is 10.001 centimeter, 10.002 centimeter, 10.003 centimeter. Okay, just by looking at these measurements, can you tell me the type of instrument from which these measurements are taken?
Scale, meter scale.
Yeah, this is meter scale. Huh? There's one decimal place. Then second one?
Vernier
Vernier
caliper.
Vernier caliper. Very good. Third one?
Screw gauge.
If I look at these measurements, then the difference between any two consecutive measurements is zero point 0.1 centimeter. The difference between any two consecutive measurements is 0.01 centimeter. Here, the difference between any two consecutive measurements is 0.011 centimeter. So, the measurements of C are closest with each other. So, this is the most precise. C is most precise. I'm repeating again, there is no relation between accuracy and precision. Precision have does not depends upon the true value. You don't even care about true value while calculating precision. Just take the separation between the measured values. If measured values are very close to each other, then you call your measurement as very precise measurements. If they are not close, then the precision is less. And precision depends upon the least count. So the instrument having minimum least count is most precise. Precision depends on least count. Instrument having minimum least count is most precise. The next thing is significant figure. Significant figure. So significant figure is basically like if I in an experiment I did an experiment and I write that the reading is 1.332 meter. Then this last digit is uncertain. You can have error while measuring this last digit. That's an uncertain digit. So this significant figure basically tells you how many significant or certain digits are in your measurement. It gives an idea about the accuracy and precision of your measurement. So significant figure. So the significant figure, the significant figures are those digits in a measured quantity in a measured quantity which are known reliably and about which we have confidence in our measurement plus one additional digit that is uncertain. One additional digit that is uncertain. That is significant figure. The significant figure basically tells you the number of digit. It gives you an idea about the accuracy and the precision of your measurement. That's significant figure. So for calculating significant figures, we have certain rules. So the first rule is all non-zero digits, are significant. All non-zero digits are significant. That means if you have a measurement like 267, just count the number of non-zero digits. 267. You have three digits, that means three significant figures. The number of significant figure doesn't depends upon decimal. Like instead of 267, even if you have 2.67, the significant figure is 1, 2, 3. You have three significant figures. So all non-zero digits are significant. That's the first rule. The second rule, if you have zeros in your measurement, then all zeros between two non-zero digits, all zeros between two non-zero digits are significant. Two non-zero digits are significant. This means if I write this as 1002, see this 1 and 2 are non-zero digits, so they are significant by rule 1. But these two zeros are in between two non-zero digits, so zeros are also significant. So in total, you have 4 significant figures. One more example, you can even have decimal 1.00101. Just have to count the number of significant figures here. 1, 1, 1. Three non-zero digits, they are significant. Now you have zeros. These two zeros are between this 1 and 1. So these zeros are between two non-zero digits. So these zeros are significant. Again, this 0 is again in between two non-zero digits. So this 0 is again significant. So total you have 6 significant figures. Next, if you have a number which is less than 1. If a number is less than 1, then all zeros to the right of decimal and to the left of first non-zero digit are not significant. So all zeros to the right of decimal and to the left of first non-zero digits are not significant. Okay, just note it down.
Thanks.
Sania?
Yes, sir, done.
This means like if I write number as 0.00123, if I'm saying number is less than 1, then it should be of this form. It can't be 1 point something because this is greater than 1. It will always be 0 point something. So if you have a number which is less than 1, then all zeros to the right of decimal and to the left of non-zero digit. First non-zero digit is this. So these three zeros are not significant. And this 0, this is never significant. So the number of significant figure, 1, the non-zero digits. So in a number, non-zero digits are always significant. We have issues with zeros only. So if you had zeros between two non-zero digits, then they are significant. But if you have 0 between decimal and first non-zero digit, then they are not significant. The number of significant figure are just 3. But in the same question, if I write this as 1.0001203, now this 0, this 0, this 0, this 0, all 4 zeros are not significant. 1, 2, and 3 are significant. But this 0 is in between 2 and 3, so this is significant also. The 0 is in between two non-zero digits. So by rule number 2, this 0 is significant. So you can say that number of total significant figure are 4. The next is if you have number in scientific notation, or not scientific notation, repeating or trailing zeros in a number without decimal are not significant. That means if the number is 10000, these are repeating zeros. You don't have decimal here, so these zeros are not at all significant. You just have one significant figure. Significant figure is one only. Even if you have 1200, these two zeros are repeating zeros. There's not decimal, so these two zeros are not significant. Only significant figure are two. But if the number have decimal, then these repeating zeros become significant. So repeating or trailing zeros in a number with decimal are significant. These zeros become significant if your number have decimal. For example, like if I write at 1.000, if I write this as 1.000, then this zero, there is decimal in the number. So these repeating zeros are significant now. So you have, in total, you have 4 significant figures. Similarly, if I write this as 21.00, you have decimal here. So these two zeros are significant now. You have 4 significant figures. So if you have a number, do you know what is scientific notation? No. See, in scientific notation, powers of 10 are not significant. Powers of 10 are not significant. Just a second. So scientific notation means the number is in this form, 1.21 into 10 raised to the power 3. Scientific notation means this form, 1.21 into 10 raised to the power 3. See, this power of 10, scientific notation means you just have one digit before decimal and then you have powers of 10. These powers of 10s are not significant. This is not significant. You will count the number of significant figures only here. So the number of significant figure are 3 only. You can even have, let's say 6.72 into 10 raised to the power minus 6. These powers are not significant. Just have to look at there. 7, 2, 3. So you have 3 significant figures. So if you have scientific notation, then the number of significant figures, in significant figures, we don't count the powers. 7. So irrational numbers, multiplier and divisors have infinite number of significant figures. Infinite number of significant figures. Multiplier and divisors means, like if I tell you that circumference of the circle is 2 pi r, then this 2 is a multiplier. This 2 is not a measured value, it's a multiplier. Whenever you measure 2, it will remain same. Means the accuracy in the measurement of 2 is infinite. So significant figure in this 2 is infinite. Similarly, if I take the volume of a sphere, this is 4 by 3 pi r cube. This 4 and 3 both, these are not measured value. They won't have error. These are just the multipliers. So you can say that significant figure in 4 is infinite. Similarly, significant figure in measurement of 3 is infinite. So these are the significant figures in the measurement of 4 and measurement of 3. After multiplier and divisor, there is one last, that if you have irrational numbers like pi and exponential have infinite number of significant figures. So this is how we count significant figures in a measurement. Okay, let's do 3 questions for each one of you. Father, this first question is for you. 2.000. How much significant figures are there? Number of significant figures here.
4.
4. Question number 2. 0.050. Noor, number of significant figures here. 2. See, this 0 and this 0 are not significant. Just have 2 significant figures. Sania, 1.002 into 10 raised to the power minus 3. Significant figures here.
4.
4. This is not significant. 1 and 2 are significant. All zeros between two non-zero digits are significant. 4 significant figures. Okay. After this, next you have some rules of rounded off. Rules for rounding off. First rule. If you want to round off a number, a digit, and that digit is less than 1, if digit to be rounded off is less than 1, preceding digit is left unchanged. So if the digit to be rounded off is less than 1, then preceding digit is left unchanged. Means, less than 5. For example, like the number is 1.243. I'm asking you to round off this 3. This 3 is less than 5, so the answer will be 1.24. So if the digit you are rounding off is less than 5, then the preceding digit is left unchanged. If digit to be rounded off is greater than 5, if digit to be rounded off is more than 5, then preceding digit is raised by 1. For example, in the same example, instead of 1.434, I give you 1.46. The 6 is greater than 5. Preceding digit is raised by 1. This is 1.25 now. But if the digit to be rounded off is 5, then you have 3 types of cases. If digit to be rounded off is 5, followed by a non-zero digit, preceding digit is raised by 1. For example, say you have 1.2351. So I'm asking you to round off this 5, round off this 5. The 5 is followed by a non-zero digit, so your preceding digit will be simply raised by 1. It will be 1.24. Similarly, it's 1.23, it's 5, let's say this is 4. I'm asking you to round off this 5. 5 is followed by a non-zero digit, so preceding digit will be left raised by 1. Now the fourth rule is, if the digit to be rounded off is 5, followed by 0 or no digit. If digit to be rounded off is 5, followed by 0 or no digit, the preceding digit is left unchanged if it is even. If the preceding digit is even, then this is left unchanged and is raised by 1 if it is odd. If your preceding digit is odd, then this is raised by 1. But if it is even, it's left unchanged. Like I'm giving you this example, 1.245. So this is 5 followed by no other digit. I'm asking you to round up this 5. Then just look at this preceding digit. This is even, leave it as it is. It's 1.24. Similarly, if I give you 1. I give you 6.885. I ask you to round off this 5. So you are supposed to round off 5 followed by nothing. Look at the preceding digit. If it is less than, this is even. So just leave it as it is. If it were odd, we will raise it by 1. Like this is 2.635. I need to round off this 5. To round off this 5, just look at the preceding digit. If preceding digit is odd, just raise it by 1. Similarly, this is 5.375. I asked you to round off this 5. Just look at the preceding digit. This is odd, so raise it by 1. Okay. The next is arithmetic operations with significant figure. Arithmetic operation with significant figure. Arithmetic operation with significant figure. The first one is addition and subtraction. Addition and subtraction. So when you add or subtract two quantities, we take care of decimal places. Like if I'm adding a quantity having 3 decimal places to another quantity having 2 decimal places, then your final result should have 2 decimal places. So the rule says in addition and subtraction, final result should have as many decimal places as are there with number having least decimal places. See a few examples. If I ask you to add 2.4642 with 1.23, just count the decimal places. Here the decimal places are 4, here the decimal places are 2. So your final result should have just 2 decimal places. So if I add them up, this is 2496.3. But the result have 4 decimal places. But the rule says your result should have the least decimal places, which is 2 in this case. First quantity have 4 decimal places, second have 2. So you will round it off up to 2 decimal places. So you'll first round this 2. This 2 is less than 5, so this will be 3.694. Sania, if I round off this 4, what will the final answer? Sania, if I round off this 4, what would be the final answer?
3.6.
Well, I'm rounding off this 4 only. So when you round off this 4,
9.
this is less than 5, so preceding will remain as it is. So the answer is 3.69. So whenever you add or subtract 2 or more quantities, just take care of decimal places. Your final result should have minimum number of decimal places. Just one more example. So I'm subtracting 6.482 from 2.1. So if I subtract them, this is 2, this is 8, this is 3, this is 4. If I count the decimal places, here the decimal places are 3, but here the decimal place is 1. You will round it off up to 1 decimal place. So if you round off 2, it comes out to be 4.38. If you round off this 8, it comes out to be 4.4. So that is the final answer. Is it clear? The first rule.
Yes, sir.
When you add or subtract, you just count the number of decimal places. The final result should have the minimum number of decimal places. And the minimum are in the numbers you are adding or subtracting. So here it's 4, here it's 2, so minimum is 2 decimal places. The next is, if instead of addition or subtraction, you have multiplication or division. In multiplication or division, instead of decimal places, we count the number of significant figure. So in multiplication and division, final result should have as many significant figure as are there with number having least significant figure. For example, so I'm asking you to multiply 1.232 into 1.4. So I'm multiplying using my calculator. So if I multiply them, 1.232 into 1.4, it comes out to be 1.7248. Now count the number of significant figure. You have 4 significant figure here and 2 here. So final result should have 2 significant figure. So just round it off up to 2. I'm doing directly. 8 is more than 5. So this 4 will become 5. When I round off this 5, okay, I'm writing all steps. So this will be 5. When I round off this 5, the digit before 5 is 2, which is even. So just leave this as it is. When I round off this 2, then the digit is less than 5. So the preceding digit is left unchanged. So that will be your final answer. Is it clear? The rule is clear? If you have more number of quantities, like if you have say 2.0, this have one significant figure. If you're multiplying these three terms, then your result should have just one significant figure. Let's do one more case. This is 4.832 over 1.31. If I'm dividing it, I'm again using my calculator for the division. 4.832, 1.31. So this comes out to be 3.6885. So if I say this numerator have 4 significant figure, denominator have 3 significant figures, so we'll round it off up to 3 significant figure. So let's round off this 5. The digit before 5 is even, so left is unchanged. Now round off this 8. So preceding digit is raised by 1, so that's 3.69. Okay, solve this question. Each side of a cube is measured to be 7.203 meter what is the surface area and volume of cube. Solve it. Each side of cube is this 7.0203. L is 7.203 meter. I need surface area. Surface area of the cube is 6 into side square, right? So that's 6 into side square. So the surface area is 6 into 7.203 into 7.203. So I'm using my calculator for the multiplication. This will be 6 into 7.203 into 7.203. So this comes out to be 311.299. Now let's count the number of significant figures. See, this is a multiplier. It's not a measurement, it's a multiplier. Sania, just tell me the number of significant figure in this 6. Sania, number of significant figure in this 6.
1.
1. This is a multiplier. Multiplier. Just check the rules for counting significant figures. Multipliers and divisors have infinite number of significant figures, right? Like this 2, this have infinite number of.
Yes.
Similarly, that 6 is a multiplier. So it have infinite number of significant figures. This have 4 significant figures. This have 4 significant figures. So what's the minimum number of significant figure? Sania, what is the minimum number of significant figure?
3.
Why 3? This have infinite. This have 4 significant figures.
Infinite.
So which one is minimum? 4, na? There's nothing like, there's no 4 significant figures minimum. So round it off up to 4 significant figures. If I round it this 9 off, if I round off this 9, this will be raised by 1. And the surface area will be 311.30. How many significant figures are there in this number? 1, 2, 3, 4. This 0 is not significant. Sorry, 0 is significant. You have to remove the 0 too. So you have 311.3. Now this is correct. This much of meter square. Similarly, when you are calculating volume, volume is side cube. So that's 2.02.
7.203 multiplied by 7.203 multiplied by 7.203. So if I multiply them, 7.203 into 7.203 into 7.203. This comes out to be 373.714. So this have 4 significant figure, this have 4 significant figure, this have 4 significant figure. So final result should have 4 significant figure. So if I round off this 4, this 1 will remain as it is. 373.71. If I round off this 1, then this 7 will remain as it is. This is 373.7 meter cube. One more question on this concept. .74 gram of substance occupies 1.2 centimeter cube. So this is mass and this is volume. Express its density Okay, calculates density. So your density is mass by volume. You take it as 5.74 divided by volume is 1.2. When you round it off, it comes out to be 4.2 gram per centimeter. Very good. So that was about significant figure. After significant figure, the next thing is error analysis. Next, you have to calculate error. See, what is error? Error is simply the difference between the true value and the measured value. Say the true value of a rod is 2 meter. When you measure the rod, your reading is 1.5 meter. So that 0.5 meter, the difference is error. So error is simply the difference between, true value, and measured value. So the difference between the true value and measured value is known as error. So error is simply true value minus measured value. That's it. So once you have calculated error, you can do statistics with the error. Once you have calculated error, you can do statistics with the error. The stats, you must have studied stats in your class 10th. Mean, median, mode. So we'll basically do stats with the error. We calculate error, then mean of error, then mode of error, and these things. Okay, the next is, now we will do types of error. The first one is mean value. Mean value, and this mean value is also known as true value. Say you do a certain measurement, like maybe you try to measure the length of the wire. You get n measurements. You get first observation is A1. Then you try to measure it again. You get the next observation as A2. Next A3, and it's up to An. So these are n readings. A1, A2, A4 up to N. So the mean value of the measurement is, it's A1, it's A2 plus A3 up to An divided by N. This is mean value, which is also known as true value. So the true value of measurement is basically the mean of all observations. After mean value, we will calculate error, basically absolute error. For calculating absolute error, we represent absolute error by delta A1. You can write this as mean value minus individual value. So once you have true value or mean value, you can take difference of mean value with A1, mean value with A2, mean value with AN and all. So the absolute error in first quantity is AM minus A1. Absolute error in second quantity is AM minus A2. Quantity is AM minus AN. That's absolute error. After absolute error, the next type of error is basically this mean absolute error. Mean absolute error means you are calculating mean of all these absolute errors. So we represent mean absolute error by delta A bar. This is mean of each of the individual error, delta A1 plus mod of delta A2 plus mod of delta AN divided by N. So that's basically mean absolute error, mod of individual errors. If you take mean of individual error, then that is mean absolute error. The modulus means even if you have absolute error in negative, this modulus will make it positive. After mean absolute error, you have another type of error which is known as relative error. This is also known as fractional error. Relative error or fractional error. So relative error is delta A bar divided by mean value. That's relative error. So relative error is basically delta A bar, mean value, this mean absolute error divided by mean values relative error or fractional error. Next, you have percentage error. Percentage error is its mean absolute error divided by mean value multiplied by 100. That's percentage. So in questions, these n observations would be given. These n observations means I give you this pen, I ask you to measure the length of the pen. So you take 5 readings. These are those 5 readings, A1, A2, A3 and all. Once you have 5 readings, the true value is mean of all. The absolute error is the difference between the mean value of and each of the individual value. This mean absolute error is basically the mean of all these individual errors. The relative error is simply that mean absolute error divided by mean value. The ratio of mean absolute error and mean value is this relative error, and the percentage error is the relative error multiplied by 100. First question on the calculation of error. So the readings of refractive indices are, so you are trying to measure the refractive index. So the readings of refractive indices are, it's 1.20, not 20, let's keep it as 1.21, 1.22 and 1.23. So these are the 3 readings of refractive indices. Calculate first mean refractive index, mean refractive index. Second, I need absolute error. Third, I need mean absolute error. Fourth, relative error. Fifth, percentage error. Sixth, answer with error limit. Report your answer with error limit. So just one more thing. If in the numerical of error, it is given that report or calculate your answer with respect to significant figure, Then while adding, subtracting, multiplying and dividing, you have to follow the rules of significant figure that we just have recently done. But if in the question the rules of significant figures are not mentioned, it's not mentioned to solve all with regards to significant figure, then you do one thing, try to keep your calculations up to 2 decimal places. You can relax the rules of significant figure, but try to keep your calculations up to 2 or 3 decimal places. Try to keep it up to 3 decimal places. So the first one, mean value, is very straightforward. Mean value is just add them up and divide by 3. It's 1.21 plus 1.22 plus 1.23 divided by 3. So the mean value comes out to be, it's 3.66 divided by 3. So the mean value comes out to be 1.22. It's 1.2. That's the mean value. The second is absolute error. The absolute error is this, delta n1. Absolute error is mean value minus n1. It's mean value minus the first value. Mean value is this 1.22 minus n1, that's 1.21. So delta n1 is 0.01. Is it clear, these first two parts? Fatma, Sania?
Yes, sir.
Yes, sir.
Next, you need absolute error in second quantity. So it's again mean value minus n2. So the absolute error in second quantity is mean value is 1.22. Second quantity is again 1.22. So there's no absolute error in second measurement. This is absolute error in first measurement. This is 0. No absolute error in second measurement. Similarly, you can calculate absolute error in third measurement. So delta n3 is, it's 1.22 minus 1.23. So if I subtract them, this is minus of 0.01. These are 3 measurements. So delta n1, delta n2, delta n3, these are 3 measurements. After this, we can calculate the mean absolute error. For mean absolute error, the relation is mod of delta n1 plus mod of delta n2 plus mod of delta n3 divided by 3. So mod of delta n1, how much is mod of delta n1? This is 0.01, this is 0, and this is minus of 0.01. So this is 0.01 plus 0. This is modulus of minus 0.01 by 3. Modulus means even if it is negative, you can make it positive. So that's 0.01 plus 0 plus 0.01 by 3. It comes out to be 0.02 by 3. So if I take this division, so it's 0.02 divided by 3. It's 0.0066. It's 0.0066. So if I round it off, you can leave it here or you can round it off up to 3 decimal place. This comes out to be 0.007. That's delta n bar. So once you have delta n bar, this is mean absolute error. You can calculate relative error. Relative error is mean absolute error divided by mean value. Mean absolute error is 0.007 by mean value. Mean value is 1.22. So this comes out to be 0.007 divided by 1.22. So if I divide them, this is 0.0057. This is relative error. After relative error, the fifth one is percentage error. Percentage error is mean absolute error by mean value multiplied by 100. So this is 0.0057 multiplied by 100. This delta n bar by nm is this. This is 0.0057 into 100. It comes out to be 0.57%. Sixth, after percentage error, you need answer with error limit. So answer with error limit means its mean value plus minus mean absolute error. So this is mean value, which is 1.22 plus minus mean absolute error, which is 0.007. So this basically means this is the value that you have measured, and this value can have this much of error, 0.007 plus or 0.007 minus. Means it can have this much of error, 0.00 minus 1.22 plus 0.007. So your actual value will lie in between these two limits. So whenever he asks you to calculate answer with error limit, so you can express that answer in one of the two ways. The first way is this, mean value plus minus mean absolute error. Or you can write this as mean value plus minus percentage error. So mean value is 1.22, percentage error is 0.57%. So this means you have measured this value, but it can have a 0.57% of percentage error, either plus or minus. Means your value could be 0.57% greater than 1.22, or it could be 0.57% less than 1.22. Okay, do one more question on the same concept, because we have to do combination of error. For combination of error, you should be the types of error should be very clear. Let's do one more question on the same concept. So I'm coming to the next slide. So the first part. If I take mean value, then mean value is simply the sum of 2.48 plus 2.46 plus 2.49, 2.50, 2.48 divided by 5. When you add them up, it comes out to be 12.41 by 5. When you divide them, the mean value comes out to be 2.482 meter. When you round it off, it's 4.48 meter. If I round off this 2, it comes out to 2.48 meter. That's the first part. Second part, after mean value, we need absolute error. So delta L1 is its mean value of L minus measured value of L. The mean value of L is 2.48. The measured value is first is 2.48. So that comes out to be 0. Its mean value minus L2. Mean value is 2.48. The error is 2.46. It comes out to be 2.02. Delta L3 is mean value minus L3. Mean value is 2.48. Measured value is 2.49. If you subtract this, it comes out to be minus 0.0. Similarly, delta L4, its mean value minus L4. Mean value is 2.48. This is 2.50 minus 0.02 meter. Delta L5, it's LM minus L5. LM is 2.48, L5 is 2.4, it's again 0. So that is the absolute error. So if you want mean absolute error, take mean of all. It's 0 plus 0.02 and all numbers in modulus. Even if it is negative, you will take the positive one. 0.01, 0.02 plus 0 divided by 5. It comes out to be 0, say 0.01, 0.02, 0.02. 0.05 by 5, it comes out to be 0.01 meter. Now, if you want to calculate percentage error is mean absolute error divided by mean value multiplied by 100. The mean absolute error is 0.01, 0.01. The mean value is 2.48. Multiplied by 100. So this is 1 by 2.48. So 1 by 2.48 is 0.40%. So now you know all types of errors. You know what is absolute error, what is mean absolute error, what is relative error, and what is percentage error. Now, the major part of this topic, the part from which you will get major questions is combination of error. Say, you know error in quantity A, you know how to calculate error in quantity B. Now you have to see how this error will combine if you add A and B, or you will subtract A and B, or you multiply A and B, or you divide A and B. Now you have to learn the combination of error. You know how to calculate the individual errors. So from now onwards, in the questions, you will be given that error in mean absolute error in A is this, mean absolute error in B is this. He will ask you to calculate mean absolute error when you add A and B. He can ask you to calculate mean absolute error if you subtract A and B. He can ask you to calculate mean absolute error if you multiply A and B. Similarly, he can ask you to calculate mean absolute error if you divide A and B. So the next major part of this chapter is combination of error. This is the portion from which you will get maximum questions. Combination of errors. What will happen to error when you combine two quantities? That's combination of error. So in combination of error, you have, let's say you have a quantity A, which is mean value plus minus delta A. See, although this delta A is the notation of absolute error, but in calculations, this is always mean absolute error. This is always mean absolute error. Even if numericals, if it is given that absolute error is something, that means mean absolute error is given. Because absolute error in each quantity is different. See, in every measurement, absolute error is different. But if he is given one absolute error for the entire measurement, that means the mean absolute error is given. And this AM is the mean value. AM is the mean value, this mean value. This mean value is AM. And this is the mean absolute error which is given. So you have a quantity A, mean value, and mean absolute error is given. Similarly, you have a quantity B, mean value and mean absolute error is given. This is mean absolute error in B, this is mean value of B. Now, if I ask you to add or subtract, addition and subtraction is easy. When you add A and B, then mean values will get added up separately. A mean value of A will get added up with mean value of A, mean value of B. And the mean absolute error of A will get added up with mean absolute error of B. So that's delta A plus delta. So when you add two quantities, you will add mean values separately and you will add error separately. There's one more thing. When you combine two quantities, we try to calculate the maximum possible error. Like while combining, if you have options, like you have two types of options, you will have delta A minus delta B and you have delta A plus delta B. These are the two types of errors which are coming. So in your answer, you will report this thing. Theoretically, we always try to calculate the maximum permissible error. We calculate maximum permissible error always. So even if you are adding or subtracting two quantities, we are trying to calculate the maximum error in the result. So this is addition. Now if I subtract them, see, this mean value will follow basic algebra. If you are adding two quantities, mean values will add. If you are subtracting two quantities, mean value will subtract. If you are multiplying or dividing two quantities, mean value is a multiply or divide. The issue here is with the error. The error does not combine with like normal numbers. For error, you should know some rules. Like when you're adding or subtracting, mean absolute error will combine. When you add or subtract two quantities, then this is the mean absolute error which combines. So when you were adding, you added the mean value and you combined the mean absolute error. When you subtract these quantities, you subtract the mean values. You subtract the mean value of A from the mean value of B. But you add the mean absolute error. Mean absolute error will not get subtracted. You will have many options. Like you will have minus delta A plus delta B. If I open this thing, you will have minus delta A minus delta B. You have delta A minus delta B. Out of this, I'm picking the one which is maximum error. That's why I'm picking this the maximum addition here. So remember, you will not never subtract error. You will always add error. And you always calculate the maximum permissible error in the quantity. So in addition and subtraction, absolute error in result is sum of absolute error of individual quantities. So whenever you add or subtract two quantities, the absolute error in the result is basically the sum of absolute error of individual quantities. So when I'm saying absolute, that means mean absolute. So let's move on to next slide. Let's do a few questions on mean abs on addition and subtraction. Say you have a temperature T1, which is 200 plus minus 0.2 Kelvin. You have a temperature T2, which is 300 plus minus 0.3 Kelvin. I ask you to calculate T2 minus T1. I ask you to calculate first part, temperature difference. Second, percentage error in that temperature difference. Percentage error in temperature difference. So you need to calculate temperature difference first. Next, you need to calculate percentage error in temperature difference. Solution. So for temperature difference, it's basically T2 minus T1. So when you subtract quantities, the mean values get subtracted. So 300 will subtract this 200. But these absolute error will get added up. You will add 0.2 and 0.3. So this T comes out to be 100 plus minus 0.5 Kelvin. Is it clear?
Yes, sir.
It's okay. In the second part, if you want to calculate percentage error is delta t by mean value multiplied by 100. When I write delta t means mean absolute error. This is the mean absolute error. Yes or no, you are correct. This is the mean value. So this is 0.5 divided by mean value multiplied by 100 gets cancelled out. So that's 0.5%. Do one more question. Your resistance are given. R1 is 100 plus minus 0.10 ohm. R2 is 500 plus minus 0.5 ohm. Calculate equivalent resistance when they are connected in series. Connected in series. So in class 10th, you must have done series and parallel combination. Series combination says R is R1 plus R2. And second, I need percentage error in R. So if I combine them, your resistance R is the algebraic sum of R1 and R2. So 100 will get added up with 500. 0.1 will get added up with 0.5. So the resistance is 500 plus minus 0.6 ohm. Oh, sorry. 600 plus minus 0.6 ohm. Second part. Now you can calculate percentage error. It's mean absolute error by mean value multiplied by 100. So it's 0.6 by 600 into 100. So that comes out to be 0.1%. So that is the mean absolute error. The second rule is for multiplication and division. The last rule is the rule of multiplication and division. So in multiplication and division, final results should have relative error in result is sum of relative error of individual quantities. So in multiplication and division, you will not combine absolute error, but you will combine relative error. So first see multiplication. So you have a quantity A, which is mean value plus minus error in it. You have another quantity B, which is mean value plus minus error in B. You're supposed to calculate a quantity C, which is the product of A and B. When you multiply C, you obtain by the product of A and B. C again have two terms like mean value plus minus error in C. C is also in this form, mean value plus minus error. If you want to calculate the mean value of C, the mean value of C is mean value of A multiplied by mean value of B. If you want to calculate error in C, then you will combine relative error. What is relative error? Absolute error by mean value. Relative error in A, which is delta A by AM, plus relative error in B, which is delta B by B. So when you multiply two quantities, then you combine their relative error. Mean value is simply the mean multiplication of mean value of A and mean value of B, but the error that we combine here is not absolute, it's relative. For example, if I give you length is 4 plus minus 0.4 meter, breadth is 2 plus minus 0.2 meter, and I ask you to calculate area with error limit. See, in this example, area is what? Area is the product of length and breadth. Area will have two terms. It's mean value of area plus minus error in area. The mean value of area is simply the product of mean value of L and mean value of B. So the mean value of L is this 4, mean value of B is this 2. So that's 4 into 2 equal to 8 meter square. Next, you can calculate error in area. The error in area is this, it's delta A over mean value of A is delta L by mean value of L, delta B by mean value of. So delta A by mean value of A, which is 8, it's delta L, which is 0.4, by mean value of L, which is 4, delta B, which is 0.2, divided by mean value of B, which is 2, delta A by 8 is 0.1 plus 0.1. So delta A is, it's 0.2, if I multiply it by 8, it's 0.16. This is the error in A, and this is the mean value of it. That if you are multiplying two quantities, you're basically combine the relative error. Okay. Similarly, if I divide two quantities, then also we will combine the relative error. Even in division, we'll combine the relative error. After multiplication, the next is division. So when you are dividing two quantities, you're basically combining this thing. Just like multiplication, you're again combining the relative error. So if I ask you to divide A and B, if I say that I have a quantity D, which is A divided by B, then the mean value of D is simply the ratio of mean value of A and mean value of B. It's mean value of A and mean value of B. The ratio is D. If you want error in D, then that error is delta D over Dm. This is relative error in D, which is delta A by Am plus delta B by Pm. So when you divide, you combine relative error. Okay, solve this question. Mass of body M is 4 plus minus 0.4 kg. Density of a body is 2 plus minus 0.2 meter cube. So this is the mean value of mass. This is error in mass. Or sorry, density. Don't. Density. This is volume. This is mean value of volume. This is error in volume. Calculate density with error limit. Okay, just note it down. It's okay. See, density is the ratio of just mass and volume. This is density, the ratio of mass and volume. The mean value of mass is this. The mean value of volume is this. Sorry. You can write your density in this form, right? It's mean value plus minus error in density. So the mean value of density is mean value of mass divided by mean value of volume. So the mean value of density is, what is mean value of mass? Mean value of mass is 4. Mean value of volume is 2. So it comes out to be 2 kg per meter. When you calculate error in density, it's delta rho by mean value, it's delta m by mean value, delta v by mean value. So a delta rho is, you are supposed to calculate, mean value is 2, delta m is 0.4, mean value is 4. Delta V is 0.2, mean value is 2. Delta rho by 2 is 0.1 plus 0.2. Delta rho by 2 is 0.2. Delta rho is 0.4. So your rho is 2 plus minus 0.4 kg per meter cube.